So good morning to all. So in the last class, we have studied about the passive transducers using inductive circuit elements, and also passive transducers using resistive circuit elements. Okay, so the transducers which are constructed based upon the circuit elements, that is passive circuit elements, resistor, capacitor, inductor. And we can also consider the active circuit elements like vacuum tubes and transistors. So previous class we have studied about the passive transducers using inductive circuit elements. In that case, we have different transducers, that is inductive transducers, variable reluctance transducer, and also important one, that is LVDT, linear variable differential transformer transducer. So all these are used for measurement of the displacement, especially for the measurement of linear displacement. For measurement of linear displacement, we can use this LVDT and variable reluctance transducers. Okay, so coming to the next type of the classification in the passive transducers, which is based upon the capacitive element. The properties of the capacitive elements are used for development of the passive transducers. So if you consider a capacitor is nothing but it is having two conductors or two plates, and in between we have a dielectric material or dielectric medium. Okay, if you consider the capacitor is nothing but it is having a two electrodes. Okay, and in between we have a dielectric medium, and that particular combination is called as a capacitor. So it will use it for the storage of the voltage. So in the below figure we have shown, that is on the right side we have a movable plate and fixed plate, and in between we have dielectric medium. So these capacitor transducers are used for measurement of the displacement. So suppose we have to measure the small displacements, and those displacement value will be converted into corresponding electrical signal by using the capacitor transducers. So in the given figure, we have one is a fixed plate and another one is a movable plate. Okay, movable plate. So the displacement, whose displacement is to be measured, that is connected to this movable plate. And if you consider the capacitor equation, the capacitance of a capacitor, C is equals to epsilon A by D. Epsilon A by D. So whereas epsilon is epsilon naught into epsilon R. So that is absolute, epsilon is the absolute permittivity, and whereas the epsilon naught is the permittivity of the free space, and epsilon is the relative permittivity. And A is the overlapping area between the two plates, and D is the distance between two plates. So based upon this formula, we can obtain the C value. So if any one parameter we can change, that causes the change in the capacitance value. So if you change the overlapping area between the two plates, the capacitance value will be changes. If the area is increases, that is overlapping area between two plates is increases, then the capacitance value is increased, because it is overlapping area is proportional to capacitance. If the distance between the two plates is increases, the capacitance is decreases, because the distance between the plate is inversely proportional to the capacitance of the capacitor. Okay, so that's why the distance increases, capacitance decreases. Inverse relationship is there. So based upon, and also there is a permittivity of the medium or observed permittivity. So if the permittivity of the capacitor will be or dielectric medium will be changes, then also the capacitance value will be changes. Based upon these three properties or variations, we can change the capacitance. Considering these three variations, okay, so we will apply the displacement. The displacement will causes the change of any of these three parameters. First of all, we have to measure the displacement. So the displacement variable is applied to the capacitor, which causes change of any of these parameters. Okay, it may be causes all the parameters may be changes. So that results change in the capacitance. So in the first figure, this figure, in the right side we have figure. So that figure we will apply the displacement to the movable plate, and fixed plate is fixed. Okay, so this plate will be moves depending upon the applied displacement. So when the distance is changes between the two plates, then the capacitance will be changes. So this is the effect of the change of the displacement. Change of the displacement. Suppose if the plate is moving to the away from this dielectric medium, then the distance will be increases. Distance increases means the capacitance will be decreases. So we will take the output between the two plates of the capacitor. So output will reflect the change of the capacitance. So the change in capacitance will be measured by using AC bridges. Okay, so that the variation of the capacitance will results to the variation of the applied displacement. And coming to the left side figure we have. So here it is having one is a fixed plate and another one is the movable plate. Movable plate. So here we will change the overlapping area. So we will change the overlapping area between the two plates. So if area is changes, the capacitance also changes. If the overlapping area between the two plates is increases, the capacitance will be increases. So like this, we can measure the change of the capacitance in terms of the displacement. So moving plate is used to move. Okay, so the displacement will be applied to the moving plate. So depending upon the displacement, the moving plate will be changes its position. And due to that, the overlapping area between the two plates will be changes that causes the change in the capacitance that relates the displacement variation. So like this, we can convert the mechanical displacement into corresponding electrical variations by using capacitive circuit elements. So these are capacitive transducers. These are called as capacitive transducers. So another type of the classification for the passive transistors based upon the uses of active circuit elements. So generally, active circuit elements are considered as vacuum tubes and transistors. Vacuum tubes and transistors are considered as active circuit elements. So generally, by using these active circuit elements, there is an advantage that the power gain will be increases. By using these transistors, the gain of the signal will be increases. So you know that the transistor is used for the amplification of the signal. So gain will be rises. So that is one of the advantages. And such elements are occasionally used as a transducers. So here the first one is variable transconductance vacuum tube. So in the olden days, the vacuum tubes will be used for amplification and as a diode, it will be used as a diode as a transistor also. So in the vacuum tube, we have a anode and cathodes. Okay, whenever there is a light falls on this cathode, it will emit the electrons. Electrons. Okay, so when these electrons will reach us to the anode, so there is a current will be short circuit will be formed, and by that the current will be passes. Okay, so based upon that principle, here we have variable transconductance vacuum tube. So it is the distance between this electrode and anode will be changes. So anode is fixed and another one is cathode. The control gate and cathode of vacuum tube are changes. So due to that, there is a between the conductance between these two will be changes. That results that will measure the displacement. So the displacement whose displacement is to be measured, it will be connected. It will be connected to this cathode of the vacuum tube. So when the displacement is changes, the cathode position is also changes, and due to that, the conductivity between the anode and cathode will be changes. That will result the output will be measured in terms of the displacement. And this is a Walden type of the measurement, and by using vacuum tubes. And nowadays the transistors are manufactured and these are used for the measurement of mechanical force. Okay, so applied to the base region of the planar transistor causes a change in the current. So the mechanical force which we are applied on the base region of the transistor, that will causes the change of the charge carriers, and due to that the current through the transistor will be changes. So the change of the current will corresponds to the applied mechanical force. So, and one of the important application for this active circuit elements is photoelectric transducers. So we can use these transistors as a photoelectric transducers in the application of the photon energy. So we will apply the photon energy to this transistor, and that causes the generation of the charge carriers. Okay. So if you consider a transistor, if you the photomultiplier, and it is a photoemissive cathode. So here photoelectric transducers are nothing but the photomultiplier tube, photoemissive cathode. Okay, photomultiplier tube, and that is consists of a cathode and anodes, and in between we have some diodes. So this is the photomultiplier tube. So it is having anode here. So this is the anode, and this light photon energy or light energy will fall on the cathode. Okay, this is the photocathode. So it will be emits some. It emits the electrons, and those electrons will fall on the diodes. These are the diodes, and once this electron will strike the diode, it will generate two electrons. It will produce as the two electrons, and these two electrons again will fall on another diode, and again it will produce as another two electrons by the two electrons. So that's why the count will be multiplies. These two electrons will produce another two electrons. This electron will produce another two electrons. Again, these electrons will strike by another diode. Again, there will be generated. Each electron will generate again two electrons. Like that, the count of the electrons will be increases. So the photon energy will be converted into electrons, and the electrons will be increased by this anode. And due to that, the finally generated electrons at the anode side will be very high. Okay, so this anode is connected to the meter, and before that we have some power supply is there. So this power supply will provide the voltage between the each diode. So it will produce a positive supply. It will produce a negative supply. By that, these electrons will move towards the forward, and by that we will get the current will be generated at the anode and cathode, and that generated current will be displayed on the output meter. So this output meter indicates the current flowing through the closed circuit from cathode to the anode. So like this, the final output of the photomultiplier tube is very high. Okay, so that current generation of current will correspond to the amount of the light energy falls on the cathode. The intensity of the light we will find out. So the sensitivity of the photomultiplier tube is very high. So, in the photomultiplier tube we have the photocathode. This is the photocathode, and this is the anode, and in between we have diodes. Okay, so these are also a positive charge carriers. We will apply the positive voltage to these diodes. That's why the electrons will be attracted towards these diodes. When this electron will struck by this diode, will produces another electron. So when struck by photons, the electrons emitted by the cathode are amplified by several stages of secondary emission electrodes called diodes. So the photomultiplier is still the most sensitive light detector. It is the most sensitive light detector. And one of its applications for biomedical purposes is that the scintillation detector for nuclear radiation used for the cancer treatment. So in the biomedical applications, we can use the radiotherapy. Okay, for treatment of the cancer, so we can use some nuclear radiation. So for that nuclear radiation, we have to use the radiation counter is there. So how much radiation amount, that radiation amount will be, or the how much radiation we are applying. So that will be to be measured. So that measurement of the radiation will be done by using this photomultiplier tube. The intensity of the light radiation of the signal, which is applied for cancer treatment. Okay, and that radiation signal will be measured by using this photomultiplier. So that's why it is one of the most sensitive detectors. So we can use for the biomedical applications. So the another one is the photodiode. So the sensitivity of photodiode can be increased if the reverse bias diode. So generally, by connecting in the reverse bias operation, the diode will be acts as a photodiode. Okay. So when the light falls on this photodiode, the junction between the PN junction will be breaks down, and due to that the charge carriers will be flows in the reverse bias direction. The current will be changes, and the amount of the current which is flowing through this diode will be corresponds to the amount of the light falls on the diode. Okay, so that's why it is photodiode. The main difference of this photodiode and Zener diode and varactor diodes and different types of diodes is nothing but the amount of the impurities we are adding to this particular pure semiconductors. That varies, changes. Okay, if the number of the amount of the impurities it changes, there is the result of different type of the diodes will be forms. Okay, so to get this photodiode, we can use the different concentration of the impurities which are to be doped to the intrinsic semiconductors or pure semiconductors. Like that, we can get the photodiode. And this photodiode will be converted into a phototransistor by connecting a base junction. So here, transistor as the collector base junction is to form a phototransistor. So photodiode will be converted into phototransistor. So by adding collector base junction. Generally, we can have all of you know that the transistor is having a PNP, emitter base collector. Similarly, for the diode, photodiode, if you add collector base junction, it will form as a transistor. So for the photodiode, this phototransistor. So at the base region of this phototransistor, we will use as this the light falls on the base region. Okay. So depending upon that, the charge carriers which are generated at the junctions of the emitter base and collector. So there is a formation of the current between the points. Okay, and from that we can identify the we can relate that current to the corresponding light intensity. So like this, we can use the photo transistor. So in this photo transistor, the photodiode current is essentially amplified by the transistor and appears at the collector multiplied by the current gain. So generally, amplifier is used for the multiplication amplification purpose. So the gain will be current gain will be amplified. So in addition to that, we have a photo Darlington arrangement. Photo Darlington arrangement. So in this, the photo transistor is connected to a second transistor. There are two transistors will be there, and these transistors are in the same substrate with the two transistors forming a Darlington circuit. So this effectively multiplies the photo current of the collector base junction of first transistor by the product of the current gain of the both the transistors. So this arrangement makes the photo Darlington is very sensitive transistor. So it will make the arrangement of the photo Darlington arrangement makes very highly sensitive. So then the next one is Hall effect transducer, or we can call it as a Hall generator. Hall generator. So in this particular Hall effect, so we have considered a semiconductor strip. Okay, it will be called as a Hall strip. Okay, so for this Hall strip, we have to send the magnetic flux, or we will apply the transverse magnetic field to this magnetic material, the semiconductor material. Okay, when the magnetic field is sent to this one side of the strip. Okay, so we have another side. Okay, another two sides we have applied the current. So here you can consider the 1 and 2 points. From 1 and 2 points, we will apply the current through this material, or we can call this strip. Okay, the current will flow through this way. We will apply some external current that is should be flow through this Hall strip, and also we will apply the magnetic field which is should pass through this strip, and then the EMF will be voltage will be generated at other side of the this strip. If we consider this strip is having a three-dimensional, okay, so one side of the strip will apply the magnetic field. Okay, so the top side of the or this front side will apply the magnetic field, and the top and bottom sides will apply the current, and the sides of this strip, right side and left side, which we connected pointers. So and from that we'll get the voltage. That voltage is called as Hall voltage. Okay, so based upon this particular principle, there is a Hall effect transducer developed. Suppose if there is any change in the magnetic field, suppose if any parameter, here we can change the magnetic field or we can change the current. If any one parameter changes, then the generated output voltage also changes. Okay. So any one parameter. So suppose the applied magnetic field was changes by the here this Hall strip, the magnetic field which is applies to this Hall strip will be changes by variation of the some displacement. Okay. So by that we can change the output voltage. That output voltage corresponds to how much displacement is applied for this strip. Okay, or how much flux variation will be causes. Okay, so suppose the flux will be changes by varying the its core position. Suppose we have a ferromagnet, so if we can vary the position of the ferromagnetic circuit, okay, so from that the flux generated will be changes, and that change in flux will be cut by this magnetic semiconductor material will be changes, and due to that the EMF will be varies. The corresponding output voltage is the corresponds to the how much of displacement which are applied to the Hall strip. Okay. So like this we have the Hall effect transducer. So these are the number of passive transducers. So if you consider the passive transducers, okay, so resistive type of the transducers, resistive, inductive, capacitive, and active circuit elements. In the resistive circuit elements, the main resistive elements are potentiometers, for photodiodes, okay, and the strain gauges. In the strain gauges, again we have two types. One is metal strain gauge, semiconductor strain gauge. In the metal strain gauge, again two types, that is unbonded strain gauge and bonded strain gauge. Okay, so like this we have passive transducers using resistive element, and similarly for coming for the inductive transducers, we have three types: inductive transducers, variable reluctance transducers, and LVDT. These are the passive transducers using inductive circuit elements. And coming to capacitor transducers, based upon the displacement and the overlapping area, so we have passive transducers. And also from active circuit elements by using the photomultiplier tube and as the phototransistors, transistors and photomultiplier tube and photodiode. All these will come under the passive transducers using active circuit elements. And also finally we have Hall effect transducers. So these are the passive transducers. So out of these, each one is used for measurement of the displacement. Okay, we will use these transducers for measurement of different physical variables. So such as displacement. Okay, so and we can use the strain, surface strain, and also we can use for the pressure. So if we consider the active transducers, so active transducers are electromagnetic induction principle based upon electromagnetic transducers, thermoelectric transducers, that is thermocouple, okay, photoelectric effect based upon that we have, and like that we have number of active transducers and passive transducers, and each one is having to measure each physical variable. So to measure the temperature, we can use this thermocouple. So like this, to measure the light intensity, how much light intensity. So we have for photovoltaic cell, okay, photoresistive, and this photodiodes, all those things. So like this, we have number of physical variables can be measured. But for measurement of the biological variables, so that is a measurement of blood pressure, fluid flow, and temperature. Okay, so all this will be not possible with this what we had explained in previous one. Okay, so what we explained in the active and passive transducers, this does not directly apply to measure the biological parameters. Okay, so that's why we have to convert the physiological variable, biological variable into the physiological variables or physical variables. Okay, so the biological variables will be converted into corresponding physiological variables or physical variables. See here the physical variables are nothing but the pressure or force, strain, okay, displacement, temperature, light. All these are the physical variables. Okay, so for the application of the biomedical applications, we have to convert the biological variables into corresponding physical variables, and from that physical variables, we can use all these active and passive transducers, and finally we get the output in terms of electrical signals, and that electrical signal corresponds to the biological variables. Okay, so the the next class we will see so what are the different transducers which are used for the biomedical applications, especially for biomedical applications. We will see. So generally, the one thing that is force transducers, and the pressure transducers are there. Okay, so for that we have a suppose this is the fixed one. In this we have a strip is there. So this is the fixed element. So in such that so there is a movable membrane. So this is the movable membrane, or we can call it as a strip. We will attach the strain gauge at this strip, and we will apply some force on this one. We will apply some force in this direction. Here, this is the strain gauge 1. This is the strain gauge 2. And this is a strip. So when we apply the force on this vertical strip, okay, so due to that, the strip will be bent. Okay. And due to that, the force will be, or the strain will be falls on both the strain gauge. The strain will be applies on the strain gauge 2, and the stress will be released in the strain gauge 1. And due to that, the output of these two strain gauges will be considered, and that will be corresponds to the amount of the force we are applied. Okay, so like this we can measure the amount of the force which is applied. Okay, so this is the force measurement. Similarly, we have this is the we can call it as a force summing element. This is the force summing element. So this force summing element is connected to the LVDT. It is connected to a LVDT. This is the LVDT. This is the primary, secondary windings, and this is secondary winding 2. This is the primary, and this is secondary 1, and secondary 2. Okay. So here we will apply the force. So these are the force transducers what we are discussing here. These are the force transducers, measurement of the force. So by the application of the force, this strip will be changes its position. It means it bends towards, suppose this is the position after applying the force. So that amount of the displacement will be applied to the LVDT. So that amount of displacement. So here we are converting the force into displacement and displacement into electrical signals. So we are applying force. This is force summing element. We can call this is a force summing element. So the amount of the force will be applied on this force summing element, and due to the application of the force, the strip will be bends its position, and the attached core of the LVDT will be also changes its position. It changes its position, and due to that, the variation of this electromagnetic core, okay, the EMF produces in the LVDT output will be changes. The generated output at output side, output at the LVDT is proportional to the amount of displacement is applied, and that displacement change corresponds to amount of the applied force, and that leads to determination of the applied force by using the electrical signals from the LVDT. Okay, so output voltage is corresponds to or calibrated in terms of the applied force. So like this, we can measure the displacement. So we are converting from one form to another form, that is mechanical form. Both are mechanical form. Force is the mechanical form, and corresponding displacement is also mechanical form. We are not directly measuring the force. We are converting into displacement. After that displacement, again it will be converted into electrical signals. Here we have